We are very happy to have Rajesh Gupta from IIT Ropar, and he'll tell us about Schwinger model on squash. Rajesh.
Okay. First, I'll thank the organizers for inviting me to talk here. Um, Honestly, actually, looking at the quality of talks here, I feel that this talk is going to be a little bit trivial. Um, so actually, before beginning, so this was the work which I did with one undergraduate student, Ashish Chahal, who is now moved to John Hopkins for his PhD. So basically, the our motivation of was slightly different. Uh, the question which we wanted to understand about the Schwinger model, because um, the Schwinger model, I mean, some of you might, or almost all of you may be knowing, there's a very old model. I mean, it's something like, I'm not so sure, probably 60s or probably some sort of. And yeah, I also don't know what was the motivation of Schwinger to introduce at that time in 2 dimension. We had study in different dimensions, but at that time in 60s, I don't know what was the motivation of studying it. But nevertheless, for a very long period, people have looked at this model. They have studied quite in detail, etc. And and yeah, so I mean, I'm sure many of you know about this, that the Schwinger model, in some sense, is trivial. Trivial in the sense that there is something called the Bosnian duality, and that Bosnian duality actually maps Schwinger model, especially the massless Schwinger model, which I will focus on in today's talk. That maps to some kind of very trivial field theory, scalar field theory. So whatever we are going to do, everything can be mapped to just a trivial. But to begin with, what puzzled to me, I mean, okay, that dictionary is fine, okay, but if you look at the Schwinger model, which is a gauge theory, etc., that has so as a trivial theory for compact boson, it's look like there's not much physics to be learned because it's just simply trivial. I mean, everything can obtain by simply weak contraction. But on the other hand, on the fermionic side, especially the Schwinger model, it is actually a gauge theory. Okay? And even though it is 2 dimension, there is a less. I mean, we expect less physics compared to the interesting space-time dimension like 4 dimension. But nevertheless, even then, one finds very rich physics. To be honest, whether it is massless or massive Schwinger model or some other deformation of Schwinger model, and you can find a quite rich physics. So our starting thing was to understand, to be honest, more deeply about the Bosnian duality, how really the Bosnian duality works. I mean, of course, mathematically we understand, but at least more concretely how the Bosnian duality is working. Okay. So in that, although I still don't have an answer to that question, I'll make it precise what I meant by that, what I wanted to understand. But nevertheless, in that process, we started to do some computation, and yeah, that was the result of this paper was a result of that calculation. Okay, so actually, 2 dimensional. So as I said, the Schwinger model is a 2 dimensional gauge theory and coupled to dynamical method. And it has, as I was saying, that it's interesting. Although people who, again, reiterating, those who knows about the Bosnian duality, they will claim that there's nothing much to be interested there because just this free field theory. But nevertheless, if you look at from the Fermionic side, there are many reasons to be interested in this. So it is, of course, simpler than the higher dimensional gauge theories, especially 4 dimensional gauge theory, which we are interested in, but it still contains some interesting physics. And therefore, one can do many. And another aspect to this theory, Schwinger model, again, so this, I want to keep my perspective here. So I have most of the thing which I'm going to talk about is in the fermionic side, just to understand the fermionic side. I'm not going to talk about the bosonic side or this free theory. And yeah, so as I said, that those who knows what the Bosnian duality, it will be more or less trivial, and the talk can be finished in 10 minutes. But yeah, so nevertheless, I will just focus on the fermionic side and just trying to understand how the bosonization is emerging, etc. Okay. Anyway, so one more aspect to this specific two dimension is that this theory, especially that it can be done perturbatively and non-perturbatively. Okay, non-perturbative computations. And I mean, this exact computation kind of thing is to me, I mean, since from my background, I have been working in supersymmetric theory for a long time. So, so for me, this exact computation is like really a realm of supersymmetric theories. But so this also the reason it attracted me towards this one, that to why fermionic side is exactly solvable. Yeah. So yeah, so as I said that in supersymmetric theories, we can do many exact computations, partition functions, index, etc. And interestingly, this Schwinger theory, even though it is not supersymmetric, even then here we can do exact computations. Okay, so the exact computations, I mean exacting coupling constant, and for all correlation functions. Okay. So as I say that this is usually the situation which belongs to supersymmetric theory whenever we heard about exact computation. But this is another example where you don't have supersymmetry, but here you can do exact computation. So I was saying that this is also the bosonization duality. And I think, again, I'm not good at history. It was probably Coleman who discovered this bosonization duality, probably, and he solved this using the bosonization duality long time back. So anyway, so in the bosonization duality, typically what happens that you map the Fermi theory to some compact scalar field, bosonic field, and to be honest, if you look at the literature, etc., many of the times, since whether it is a Schwinger model or Schwinger theory model or massive one or massless one, many of the times in the literature, people just go to the bosonic theory because there it is much easier to do the computations, okay? Because it is just a free field theory or some massive theory on scalar field. Okay, but for my thing, I will stick to just a fermionic theory.
When you say fermionic theory, in the theory
Or
variance.
Yeah, so no, gauge theory. Yeah. Okay, so now
Just to ask,
Yeah.
so you said the fermionic side has this rich structure. But if it maps to a free theory, what do the free structures map to?
yeah, and that's true. That's true. So actually, okay, so let me this is the slide I was going to talk about. So okay, so as I said that okay, so this discussion, whatever I'm going to say, it's not very precise, not very rigorous, but just to give you the feeling of it. Okay, so then it will also be clear that okay, what physics we're talking about, what physics maps to what. Okay. So when you're looking for the gauge theory, this what rich physics is that the Schwinger model, or let's say some variation of the Schwinger model, okay, that can exhibit these phenomena like confinement, screening of charges, chiral symmetry breaking, etc. These are the interesting property we want to understand in four-dimensional gauge theory, and whether we can make a really quantitative analysis, right? And here one can really make a quantitative analysis. Okay? So yeah, so these are the properties which you would like to understand in four-dimension. Okay, and there's a so Schwinger model and the variations of a Schwinger model, like you can introduce the Thirring term, you can introduce a mass term, etc. The simplest one of is just massless case. And in the massless case, it is just U1 gauge theory, two-dimensional QED. Okay, so U1 gauge theory coupled to just a single massless Dirac Fermi. Okay, so that's the thing. Okay. Yeah, so actually, so I'm going to give you some flavor of it in flat space before moving to curved space. How it has some interesting physics. So okay, so before even adding this dynamical matter, one can also just study the pure gauge theory. Okay, now pure gauge theory has these characteristics. Okay, there's no magnetic field. It's of course there's no dynamical degrees of freedom. They just electric field, and if you solve just simple equations, or let's say let's suppose if you want to understand what is the potential between the two test charges, etc., you'll find that it is confining because the electric field will come out to be constant, so the potential will has to be linear in position. Okay, so therefore, in 2 dimension, this will if you put a two test charge separate by some distance, and if you calculate what is the potential, and then it will go linearly with the separation. So that's like a confinement. So 2 dimension is very please shows the confinement. Okay, but now let's add some fermionic term, psi bar gamma mu mu psi, and then see how what new thing we can learn, and that's the of course Schwinger model. So okay, so as I said, what I'm going to say right now, it's very rough, but one can make it more precise, at least in a quantum field theoretic sense. So let's suppose you work in some case where you think of mu as some kind of epsilon mu del nu phi, because we are working in 2 dimensions, and the 2 dimensions something like a host composition. You can write it in terms of a longitudinal component, which is like a pure gauge, and then the transverse component, which is just this part. And if you okay, so I have not sorry, I should have written down the Dirac operator. Yeah, so this Dirac operator is just simply nothing but if you remember just simply this one. Of course, one has to add a spin connection later on, but right now just this part. And if you just plug this mu in this part, you see that this phi can be removed as simple Carrier transformation. Okay, just this Carrier rotation, and that can completely remove this gauge field dependence in the time. Okay. Now, if it removes the kinetic term, then we know that since it is a Carrier transformation, so it will generate some Carrier anomaly. Okay, and the Carrier anomaly will be just simply phi, the transformation, times the field strength of the gauge field, and this I can roughly write it is of the form f 1 over del square f. Okay, because this phi is nothing but just 1 over del square f. It's nothing but just f times 1 over del square f. Okay, and therefore, if you see that if you try to see what is the effective action for the gauge field, if I have integrated out the dynamical matter, then the effective action of the gauge theory in 2 dimension just becomes something like this. Okay, so this is just the Carrier anomaly part, which we have obtained from integrating out the fermions, and this is the original half f. Okay.
Can you explain once again what does the 1 by del square come from?
Okay. Actually, okay. I mean, okay. So I just said that one can make it very precise, but okay, I'm just doing roughly. So if you look at f phi, so epsilon mu f mu. So if you remember, so phi was defined in this mu or del nu of phi. So if you do the field strength, that not exactly, I mean, epsilon mu f mu, this will come out with del square. So yeah, so
del is 0. Del dot A is 0.
Del dot A is 0. Yeah, it's a transverse scale. This is my okay. So therefore, it's something like of this form f 1 over del square f. And if you now if you look at this again, I'm very not very precise here, but it at the end of the day it tells you the right physics. That if you look at this and do some integration of parts, etc., you write it in terms of A. Okay, you see that this part you can write it in this form. Okay, so this is nothing but a situation where we have a in some case where this you can drop it to 0. This is like a Proctor Lagrange, right? This is like a massive vector field, vector field with mass given by E square over pi. Okay. So, so therefore, what we understand that if we consider this massless theory, massless Schwinger model, then really the physics it described is in the Higgs phase, right? The gauge field now has a mass, and the mass is given by just this coupling. Okay. And as you understand that since now there's a mass to the gauge field, so the potential will no longer be linear, right? So the potential has to fall off because of the mass term. And you see here that if you consider two test charge and again ask the question of what is the potential between the two test charges, then what we find that the potential energy falls like something like this manner. Okay, so this is a two test charge, and then this is a potential energy between the two. And if you look at this, so this is, I'm considering the two test charge separated by distance a. Okay, so this is a potential energy between the two test charge. And you see now that if you plot it with the separation, as you increase the separation, initially it is growing, but after certain distance, it saturates. Okay, so that's like a screening. I mean, that's like a screening phenomena, and it grows to constant rather than going linear. Okay, so this is the phenomena of what we call the charge screening in the QCD. So you see that this is the situation which describes the gas state in a deconfined phase. Okay, there is no confinement here. So if you consider pure gas theory, so we started with something like a confinement, some sort of potential, and then if you have dynamical matter, massless fermionic field, then we see that now this situation is slightly different. It is in the X phase, and now we have a deconfined phase. Deconfined, I mean, in the sense that if you consider the two test charts and look at how the potential energy grows as you increase the separation, then it doesn't grow as linear. That's what I meant by the deconfined.
Simple question. So, if you have dynamical matter in any case theory, this test charge probe will always behave like this because you create particles and antimatters.
But that's
So, why is it a diagnostic of anything?
no, but that's not what we expect in the, let's say, QCD.
No, I don't know about PCB, like anything.
Okay.
You take a test charge, you just pull it out, right? So, in a certain length scale, you grow, let's say, linearly, but after a while, won't you produce particles and antiparticles?
Okay, fine. I'm going to answer in the next slide actually, about this question. Okay, so you're right here that this is what is physical interpretation, that it is screened because of it producing particle antiparticle, and then the charges are screened. So this is what and you are perfectly right. Okay, but now let's do the thing that the whatever we consider the fermionic field, we had started with a massless one, but now let's give a mass. Okay, now if you give a mass, then and you do the same analysis. Okay, so you have so the problem is like we have a again the same Dirac fermion, but now with a mass term m. Earlier we had considered the it to be a massless situation, but now we consider a massive situation. Okay, now what is happening in that it provides some sort of IR cutoff. Okay, so this gives like 1 over del square plus m. So I'm again looking at the you integrate out the fermions and again look at the effective action for the gauge spread. So this is what effective. Okay, so another thing. There are many terms here. So I'm just looking at the leading term. Okay. So now in this case, if you look at this calculation, and now if you look at the low energy physics, okay, with long wavelength region, then you see that this is nothing but this term. Okay.
Yeah, sorry,
Yeah.
I'm reading this question.
Okay.
So, this additional term that you are getting, you are
Right.
getting from the measure, was that the point because you mentioned anomaly? This additional term
No,
that
no.
you're getting.
No.
It is
Actually,
from integrating out the direct fermion?
yeah,
or
integrated from
adding-
Dirac fermion.
And then it is not related to any anomalies.
No, not anybody. Actually, no, sorry. I was talking about in the chiral case, which is a massless case. So there I can do it.
There,
That
there
you
you
can-
can do it with wide fermions only, chiral fermions, then only you'll get this term, right?
Okay, yeah. So that here we were considering a massless situation.
Master situation, you can consider the chiral, some wide fermions here,
Yeah,
and then.
and you can do that. Yeah,
measure will
exactly.
generate this
Right,
term,
right, exactly. Yeah.
That measure will generate probably what kind of term? F.
Yeah. So it will
it
generate,
be
yeah,
F square only, right?
yeah, F 5 times F,
Yeah.
because it generates theta terms, right?
Okay.
Yeah. So that is the 5 times F it will generate, and that's what.
But if you have a direct fermion,
Yeah.
that thing is not because it will cancel, right?
Yeah, that is true. I mean, if the zero modes don't match, then of course it will not cancel. But if it is matching or there are no zero modes, then there will be no anomaly.
But then what is this term? How do you get it? With the direct fermion with the massive case?
Okay, as I was saying, massive case. Okay, no. So here I'm not doing those that argument. This chiral rotation argument I'm not doing.
Okay.
Sorry. So here it is really a perturbative calculation.
Acha.
In
So
the
integrating out the formula.
Yeah, integrating a formula like in one PI kind of thing, you're doing the loop calculation and then do it. Yeah. That picture I was presenting by chiral rotation was for massless space.
Okay.
Yeah. So yeah, I agree. Yeah, sorry. Okay. So now, so this, of course, actually, this is not the complete action. Okay. So there's many more terms. More terms. So I'm just looking at the, let's say, small e. Okay. Okay. So now, if we, if you look at this effective action, very small e, and if you consider low energy, IR physics, long wavelength physics, then you see that effectively what happening is gauge field, the charges are just normalized. Okay. There is no more mass term for the gauge field, so it is really still in the Coulomb phase. So it is again in the confined phase. Okay, I guess I hope did I answer your question or no? So this is here the one case where I'm giving a mass to dynamical matter, and if I look at the physics lower than that mass, then still it is a confined phase.
And what had happened in the other case when we started with the master's Girard? Was it in the
Deconfined phase, yeah.
But I'm just confused about this. Okay, that may be true, but then maybe you need some other observable to distinguish.
So yeah, so
your
another
test
observer-
charges cannot.
Yeah, okay,
distinguish.
good. Yeah, you're right.
Yeah, okay, so that was my confusion.
Yeah, no, yeah. So other thing which you can do is like Wilson loop kind of calculation.
Yeah. Okay,
Yeah.
no, my
That's-
confusion was that test charges cannot.
Right.
distinguish this,
All right. Just alone test charge will not give the evidence of this confinement decay. That's true. That I.
That's
Okay. So yeah. So anyway, so these were two different situations in two-dimensional gauge theory and how confinement, deconfinement situations arise by just considering different kind of deformations. Okay. Anyway, so as I was saying that there is no Higgs phenomena here, charges are not spin, and as I said, although this is not good enough, but nevertheless, if you consider the potential between the two test charges, then it will grow linear. You can do also the Wilson loop calculations. It will grow. It will have now area law behavior, unlike in the case of Schwinger case, master Schwinger case, where it will perimeter law behavior. Okay, so it really describes the theory in a confinement. Okay. So yeah. Anyway, so this is a very brief. Actually, just giving it about the Schwinger model, and there are many other things. For example, the bosonization duality, etc. But I will not go into that because if I speak in terms of boson theory, then all this talk can be finished in 10 minutes. So I'm just sticking to the harmonic side. So what I'm going to now do is that I'm going to put this theory in some curved space time, especially curved Euclidean space. And so when we, and there is many reasons why we want to understand, why we want to learn theory on a curved space. So one is that when you compute physical quantities, like for example, partition function or correlation functions, they will be functional of this background. So when I say, okay, I just also want to point out that, so when I say curved space, I don't just mean take a non-trivial metric, but you can also turn on some non-trivial background, let's say chemical potential, etc. Okay. So then basically the idea, what is the idea here is that you can compute quantities, whatever the partition functions or correlation function, and they will come out as a function of these background fields, so as a function. And therefore, by understanding their behavior as a function of the background, one can get a finer details about the theories. Okay. So, so for example, of course, like if you want to see really the central charge, like anomalies or index calculus, it is always good at, if you work in a flat space, you will not see those. So you have to go to the curved space to see all this, right?
Yeah, just before you go there, Rajesh, I mean, so this, you said the Thomas the permanent theory has, where confinement, phase transition, and so on and so forth. What happens when this bosonization? This, I mean, where is the signature that this? I mean, if I were just the sort of free sort of.
Yeah, so, yeah.
I mean, how would I never know that there exists a description?
Yeah, that's true.
Like
that's a very good question. Actually, that's all these things are hidden in the bosonization. When you, that's what I say. So when you look at the scalar field theory, of course, you don't know anything about the bosonide, I mean,
Right.
about this confinement deconfinement. So basically, okay, first of all, I don't, as I said, that I don't understand fully about this duality, but just to say that if you consider, okay, I hope I remember all those things. So massless Schwinger model, if you consider, then it maps to, so massless Schwinger model means fermions coupled to a U1 gas theory. That maps to a compact, massive scalar field. So that's the physics, that scalar field, in some sense, so we understand, if you can, just finish. Yeah. So this scalar field is basically what it describes is a longitudinal mode of the gauge field. Because here you see that it is in Higgs space, so the gauge field is massive, and there's a mass which is E over pi, and that's exactly that. But that's it. There's nothing more than that. So in the sense that this is in the there's no phase transition here clearly, because to begin with there's no mass, so it's just in one phase, and the only spectrum you have is just this massive field. Okay, and that's the in-bosonization. Okay. Now if you consider a massive one, let's say if you consider a massive Schwinger model, now that becomes very interesting, because as we also see in the massive case, it's like really confined. Then the massive Schwinger model maps to massive Sine-Gordon theory. Okay. Okay. And massive Sine-Gordon theory. Okay. So this statement I still don't understand very well, and the statement is that since massive Schwinger model is not exactly solvable. I don't know what does it mean exactly. So I mean, I feel that someone one day will wake up and solve it. maybe there is some way quantitatively saying that it's not solvable, maybe. But yeah, so that maps to massive thing. And here in the fermionic side, since since it is confined, the only physical quantities are like mesons, because it's confined, so cannot have a fermion. So only physical quantities are the mesons, and that mesons are like a spectrum in the Sine-Gordon scalar field excitations. Yeah. So that's something like this. But yeah, more than that, I still don't understand very well actually about this thing. Anyway, any more questions? Okay. Yeah. So, but actually, as I said, that there's no really I don't know whether there's really a phase transition, because there's no renormalization taking place in the mass. So if mass has really become a parameter. This mass maps to the coefficient. So Sine-Gordon theory is like cosine potential. So it becomes like coefficient of that cosine potential, and I don't think it renormalized. So I mean, it stays in that phase. So yeah. Okay. Okay. So yeah. Sorry. So I was coming back to this. So okay. So what I'm going to talk about is putting this theory on some curved space, and then try to see if I can retrieve some finer details about the theory, etc. And also to more to learn about how an interacting theory, like especially Schwinger model, which is an interacting theory, via fermions coupled to gas theory, somehow become trivial. Okay. So yeah. Okay. So so now here I'm going to specify what really I'm interested in. Okay. Although the original question which I had in my mind, that I still don't have an answer to, but at least one calculation which we did, so that's I'm going to talk about. So so suppose, okay, so let's suppose we are studying some quantum field theory or compound field theory on some compact space with some metric G mean. Okay. So the one quantity which we are going to our interest of this partition function. Okay, so this is okay. So one quantity which is we are interested in is just this partition function, which is just simply the integration for a fixed on a fixed background G. And then what we are looking for is that, let's suppose we consider this deformation. in the method. That is in G menu, I write it as a some G naught menu plus epsilon H. Okay. And see how this partition function, or not only partition function, correlation function, they see this the variation. Okay. So so I mean, so if once you introduce this expansion, epsilon as an expansion parameter, let's say if you use it as an expansion parameter, and if you look at the response of this partition function, or let's say 1-point function, then what we see that the partition function, the response of this partition function is contained in this to first order. Higher order will be higher point correlation functions, but to first order, it contains 1-point function of energy mounted tensor. And let's suppose if you're looking for some operator on 1-point function, then you see that to first order, it contains the information about the 2-point function involving the energy mounted tensor. Okay. So therefore, of course, it's not like just a 1-point function. Of course, it is integrated over. So it is this integrated over quantity which is contained here. Same thing about this point. So you see that if we able to compute partition function as a function of this parameter epsilon, then varying this parameter, I can obtain the information about the 1-point function energy mounted tensor, or let's say in the correlation function or 1-point function, I can obtain the information about the these correlation functions. Okay, and of course it depends on how good I am in the calculation. So the more and more I can go further if you contain more and more higher order correlation function involving energy mounted tensor. Okay, so this is just one such a deformation, metric deformation. So that will turn on the energy mounted tensor, but one can of course repeat this with any other background field. And looking, if we able to do exact computation, then we can understand the responses or calculate the responses of the of various quantities. Okay.
The background metric, it's not zero, the 1-point function.
Okay, I mean, if you consider flat space, then of course it is zero. If you consider, okay, I mean, in the sense, sorry. So if you consider conformal field theory, then of course the 1-point function on the flat space will be zero. Okay, but for a generic quantum field theory, it is not necessary. Right? Okay, so let me be more specific. So suppose
general quantum theory, even this translation invariance will not on the value will not make the 1-point function zero.
No, it will make you constant, but not zero.
Make it constant.
Yeah.
And that will never make it.
Yeah, so that constant is an interesting quantity to compute 1-point function. Anyway, yeah. Okay. So let me go back. Go to directly to the problem which we have. So what we are going to talk about is something called the squash sphere. And we are going to put our Schwinger model and one deformation of Schwinger model on the squash sphere. Okay. So why I'm squashing? So what is I'm squashing? Basically, I mean, it's squashing. It's just like a ellipsoid. If we embed this sphere, it's like an ellipsoid in 3 dimensions. So there is a parameter B, which is called the squashing parameter. So if B you set it to 0, we get back sphere. But if B is not equal to 0, then it is a ellipsoid. And one can induce a metric on this, which is has this kind of form. So one could consider generic deformation as well, and a generic background as well, a generic squashed manifold, 2-dimensional manifold. But I'm considering this simpler one. And one reason why simpler one I'm considering because even this one is not simple. I mean, although it looks it's a 2-dimensional case, but and surprisingly for this 2-dimensional case, we still don't know the full spectrum of Laplacian. So we don't have eigenvalues of all the eigenvalues of Laplacian on this space. But nevertheless, so one particular considering general
Dealing with the deformation.
with f theta, yeah. Right. So f theta here is given by this quantity, square root 1 plus b square sine. And with this, we don't have a complete. Sorry.
The dimension has been always like multiple.
Yeah, that's
So, then I know the question. Until go back, if you go to this. Conformal matrix. This should be a quantum transformation that.
That's true. I'll also talk about this Fourier transformation, which can be
So,
actually.
so then if I know things in the conformal way, then I should be able to come back and solve it.
So, heat kernel will have a non-local. You might not try it for
You
every.
may have non-local if you say the conformal matrix.
In principle, you can write down.
So that's the heat kernel coefficients will do that.
Yeah.
No, but you're talking about what, eigenfunctions? You're talking
So
about-
the Laplacian
Yeah,
problem could not be solved.
Yeah, I mean, I'm saying that-
Solve it in a conformal,
No,
why can't they come by that?
oh, but I don't
There
think
must
you
be a
can solve,
reason.
but I don't think you can solve with eigenvalue problem, using conformal transformation. Can you do it? I don't think so. By conformal transformation, you can't solve the eigenvalue problem. Okay, maybe you can say, anyway,
So you want all the modes of the Laplace.
I mean, let's,
All the Laplace equations.
no, not the Laplace, all the modes of Laplace.
So then go, yeah.
Okay, so yeah, so one of course has a symmetry of this, that it has one symmetry which is U1, which is the preserved. I mean this breaks rest of symmetry except U1. And if we now go back to this what deformation I'm talking about here, G0 plus epsilon h mu, then compared to sphere, you see that this h mu, I can take it. I mean, if you just expand this metric, we have this kind of form, right? Just it has only theta component. So basically, this is deformation away from the sphere, okay, to sphere, okay. Okay, so it is just writing. Okay, just to tell you that okay, topologically it is same as the sphere because Euler character is 2, and it's perfectly smooth manifold.
Sorry, but this H theta,
Yeah,
even if you linearize in B, we start from B square.
yeah, it will start B square. I mean, yeah, this I parameterize like B square, but yeah, I mean you
No,
could
but
write.
then how are you writing an H mu?
So epsilon here is just B square.
But G mu 0 is just the two sphere.
Yeah,
It should be the G theta 0 is 1.
G theta 0 is 1. Yeah,
But that then for that H theta,
yeah,
all my correction will come from B square.
that's true. Starting with B square order.
But then this H theta is in which order? The sine
B
theta
square,
by
B square, B square order. Epsilon is B
Why are
square.
you writing-
Oh, sorry. Bit 4. Sorry. You're right. Thank you. Sorry. No, sorry. Yeah. So actually, okay, maybe it is a bad notation. I should have called it B. Then it will start B. Sorry.
There's a typo.
There's typo. Sorry.
No, probably it means B square is epsilon, right?
B square is epsilon.
So
Yes.
that will be B square H which is.
No, but then I should write order B.
Bit 4. Yeah.
B square H is B four.
But that was not in the first.
No, he goes epsilon H.
Okay. Good.
Sorry. There's a typo.
Okay.
That's what I see.
Okay. That's true. Yeah. This is B square order.
And the next
That's
time he has.
okay. That's true.
Ah.
Okay. So thank you. Okay. Anyway, okay. So we can just plug it back and see see how the partition function look like. So partition function, of course, will contain this t theta component, and similarly the correlation function will have just t theta component. Okay, so this is of course for generic quantum field theory or any quantum field theory, and now if you consider, let's suppose if it's specialized to let's say conformal field theory, then on a sphere we know that this t mu 1-point function is non-zero, unlike the flat space, and it's just proportional to the central charge t, right? So what we see that for conformal field theory, if we consider, then the partition function, if we for any conformal field theory, if you're able to calculate it, then first B square can give me the central charge of the three. Okay, and similarly,
Why some of my function was there?
no, I'm not talking flat metric. I'm talking sphere.
Okay, so
Oh, sorry. You mean okay? Sorry, I have put here the sphere radius 1. Is that the question you're asking?
Okay, yeah, so the perturbation is around
Yeah, partition around the unsquare sphere. Yeah, exactly. Yeah. Sorry, I put okay. So I've considered just one the radius of the sphere. Yeah, equal to 1. So in that unit we're working. Okay, it's fine. Okay, so okay, anyway, so let me just give some results here. So okay, as a first step, one could do this calculation as cost pair. Let's say for free field theories. Okay, just simply free field theory. For example, master scalar or master Dirac Fermi, etc. And then what we can find, you can explicitly calculate this. Either you can use the heat kernel methods, or you can use the eigenvalues, where you can find out the correction to eigenvalues in perturbation expansion. And then you have to, I guess, anyway. And you have to just, okay, anyway, so all those calculations you can do, and there will be some infinities in this calculation, you have to regularize, etc. But bottom line is that, for example, if you consider massless scalar field theory, then it comes out to B square 18. Of course, this corresponds A equal to 1. Similarly, for massless Dirac fermion, you get similar thing, B square 18. And for if you consider, let's say, Dirac fermion in presence of monopole background, this monopole background will be of interest to me later on. Then the only correction comes here with here in 3p. Okay, so here P is a turn on the magnetic flux through this cross pair. So that also contributes to this variation in the partition function, and that comes as 3. Okay. P is the magnetic. Sorry. Yeah. So I'm considering now the fermions in presence of monopole. Okay. So then the first variation will the central charge, or let's say that will also receive correction because of the. Okay, yeah. So yeah. Anyway, so here I was thinking of giving some detail, but it's not important. But basically, you can one way of doing is just to use find the correction to the eigen values. This correction will be just given sandwiching between the original eigen functions. Whatever the correction operator you have, you just compute this quantity inner product, and then you can compute this variation in the partition function. Of course, one thing is that you have to do this in a summation, and you have to regularize it. But yeah, so there you go. So this is a small detail. Okay, now let's come back to the Schwinger model. So now, so we are going to put this Schwinger model on a cost sphere. Okay, so whatever the calculation we have done, we want to do for the Schwinger model. Only difference is now the interacting, and of course, we wanted to understand that how this interacting model suddenly becomes solvable. Okay. So, so anyway, so this is just a notation. So these are Dirac.
Just one question, just make sure. So the Schwinger model maps to the massive
Compact scalar, yeah.
no, massive sine Gordon.
No. Schwinger model massive compact scalar.
You mentioned something about the sine Gordon.
Massive Schwinger model maps to sine Gordon.
Okay, but the sine Gordon model is not easily solvable, right? Or is it?
Okay. I think it's not. I think I'm not so sure. I think the massless sine Gordon
That
is
solvable.
yeah.
That's just a free theory. But when you put on
No,
that
it's not a free theory. That sine Gordon
so sine Gordon is grad phi whole square
plus
plus some cos
phi.
phi.
Yeah.
Right?
That's
So,
I think integrable, right?
If I switch, that's integrable.
Yeah.
So if I switch off cos phi, then of course.
Yeah. That's a simple.
But with the cos phi also. Oh, yeah. It's integrable. Yes.
Oh, still I don't know what does solvable, non-solvable mean. Anyway,
What is solving?
yeah, exactly.
No, but integrability has a specific.
Yeah, exactly. Yes. Yeah. Okay. So another thing, one could like whether you can add theta term here, but we don't need to add because we are considering massless fermions. So we don't need to add theta term because any such theta term we can remove by just chiral transformations. Yeah. So we don't need to add a theta term. Okay, so now let's come to the crux of the issue. So when you consider this gauge theory on this 2 dimension, and we consider the partition function, let's suppose, Then we have to integrate out, of course, integrate about fermions, but we have to also integrate about all the gauge field configurations. Okay. And if you look at the gauge field configurations on a sphere, then they have a topological sectors. Okay, so the topological sectors, I mean that I'll write on the expression, but topological sector means that the gauge field you have to turn on the fluxes. Okay, and these fluxes are quantized. Okay, so as a result, what happens yeah, so I mean there is similar analog in the Euclidean space where you have instanton backgrounds. Okay. And if you consider on the compact space, then you have a flux. Okay, so what will happen that as a result that if you can do any computation, if you want to do any computations on this curved space, then you can organize this computation as a sum. Okay, sum over all these topological sectors. Okay, similarly, like for example, whether it is a partition function or whether it is a 1-point function or a 2-point function. So you can organize this in terms of each topological sector. So here it becomes like a really infinite sum. Okay.
Sorry, are you considering abelian, Schwinger, or non-abelian?
Non-abelian, I'm not talking about here, just abelian.
So, even for the abelian, you would have this non-abelian sector.
Yeah, exactly. Yeah. So you have to turn on the Okay. Okay, so therefore this boils down, and it's okay. So I mean, if you think about, I mean, again, if you if I tell you my perspective, it's still very surprising that this is on the right hand side supposed to be some trivial theory.
Yeah, exactly.
But here it is.
Which is the thing that is, I think, the most surprising of all, right?
That's
Because you're saying all of these things which seem to be very non-trivial,
exactly.
and on the other hand,
It's
say
very
that
trivial.
you do a Bosonization
And it becomes trivial.
and everything becomes trivial. I don't understand it.
No, non-trivial theory is the phase transition.
Which non-trivial theory?
In the fermionic theory,
There is some phase transition.
I mean, I don't know if he's treating the mass as a parameter or not. It's clearly two, phases, right?
No, okay, I'm going to focus only on the massless case. So mass, so once it is massless, it will always remain massless.
Yeah. So I
So
mean, if there is a way that you can tune the mass, then of course
Then there will be
can
phase
see
transition. Yeah.
But there are two distinct phases of this thing.
Once you're in one phase, you have to stick to that phase.
Yeah.
Yeah.
So there is no phase transition even in the fermionic theory as such.
No.
Until and unless you sort of do something
Do something
boring,
to mass
or
and
put some operator.
vacuum. I mean,
One is changing the vacuum here from not because the wave that is writing is different from the raptures of that. Or I'm missing something.
no, I didn't understand.
I'm saying that when you bosonize the system,
Yeah.
you don't change the vacuum. You only do the calculation.
But,
in a different
I mean,
way.
it's exponential.
Compared to what you were issuing.
Yeah.
Maybe it becomes like a coherent state, right? Something sort of collapse to.
I would totally expect the vacuum to change, or I might be missing something.
Maybe
Convention function is just simplicity.
Yeah.
Exact person.
That's true.
Here it's clearly the opposite. The zero is a very purpose. There is 1.2.
No, Bosonization is a non-trivial transformation, but once you do the transformation correctly, you should get the.
When you transform it in a cardinal language, that's a very complicated cardinal. That might have a. So that's changing the record. I'll say that you are changing the field.
Yeah, exactly. I will not change the. I don't know why. Yeah.
You're changing the operator.
Exactly. Yeah.
It's like e power phi something.
Yeah. Exactly.
it's not
Actually,
vertex operator like
It's like a different operator and it's like there is a difference. Or it's a.
No, sorry. So I'm just saying that for each.
It's technically the generic.
Yeah. Right. Okay. Yeah. Anyway, so this is the curious things that suddenly. I mean, it becomes much more richer in the massive case, but okay, we'll not go into that.
But what will happen if one does a complex scalar with a kind of a scalar
Scalar QED. Yeah. Okay, that's a good question. So, I don't know, but actually there, okay, you mean, this bosonization you're talking about? Not bosonization.
But let's say,
So instead instead of the formula.
Yeah, no, but actually this is, okay, actually, this is a good question. Actually, that's the, okay, I want to come to this point actually, because this actually is the heart of this, is that how come, it looks, the way I'm presenting as if like it is a really a complicated problem, but suddenly becomes a non-trivial. So, yeah, so there, I have two insights maybe, I don't know whether it is useful, but I think that's the reason why it is. And in the, one of the thing is that is missing for scalar.
I mean, a complex scalar is like a phi 1 plus I phi 2,
Yeah.
two real scalars.
Yeah.
So that might can capture the.
Okay, I'll come to it actually. Yeah. Okay. Okay, I mean, because actually the reason, so, okay, that's the next slide. How come this infinite sum somehow becomes, I mean, either tractable, right? I mean, so and the reason is just this one, the zero mode. That is missing in the scalar case. So what happens is that if you look at the fermions on a monopole background, they have a zero modes. Okay, and one trivially sees by just doing the index calculation. Okay, because the index of the Dirac operator on a monopole background just give you P, chart. So that's tell you that there are zero modes. But and actually, yeah, and but you explicit calculation. Okay, so this is just to tell you that the difference of chiral zero modes is P, but you can actually do the calculation of these zero modes, and you can show that all the zero mode, let's say on the sphere, let's suppose on the sphere, first let's talk about the sphere. On the sphere, it has just for positive P, you have a positive chiral zero modes, and for negative P, you have a negative chiral zero modes. So the zero modes are really chiral. Okay. So what? Yeah. So I've said here the same thing. So so positive P, you have just a P number of positive chiral, and for negative P, you have just a negative. So as in, what happens that because there are zero modes, this partition function, it doesn't have infinite sum. It receives contribution only from P equal to 0. Okay. Because the point is that for higher P, you have to integrate over the fermion zero modes, and you don't have anything to absorb the fermion zero modes. Okay. So therefore, in the partition function, it will receive contribution only from P equal to 0. Okay. So partition function vanishes for if you have P not equal to 0. Okay. 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 I will come back to the 1-point function also in a moment.
Don't you also consider zero mode of the case field? Or would be
Case field zero mode. I don't think there's zero mode in the case field on the S2.
similarly will be an operator. Vision of motion.
I mean, no. Okay. I mean, other than okay, I don't know. Probably, I don't know what zero modes. Yeah. I mean, there are, of course. Actually, I'll show you some decomposition in a moment when I come to the calculation. How much time do we have?
You have enough.
I have enough, no? I start
40 minutes.
40 minutes. Okay.
Well, for some reason, the zero mode of the gauge field is important, but in this case, because there's an effective way of writing where it's massive, it's probably not given. I don't know. I was wondering about this.
But I don't know what zero modes you're talking about. Case field.
Just a constant, gauge field is constant. So it's, then it will be characterized by, constant, different constants, which will be like.
But actually, on a S2, you cannot have a case field which is a constant.
Like, some, this phi is like a constant.
No. On S2, you cannot have a smooth constant gauge field. I'm on S2. Always on S2. S2 or sparse S2, but compact space.
Constant you can have, not vector. Constant I can't, scalar field I can't have.
The scalar field you can have constant.
So that phi that you after gate choice that you have.
No, but
you
then
can have more than just
so-
phi constant. Right?
but that's derivative of phi, no? So that mu is del mu of phi. So that
It
is
is getting a phi, but you can't have a mode where phi is a constant.
so that is 0, right?
You know, that's why
Okay. Yeah, okay. So yeah, just to say about this, that even if you consider squashing, just to add, just to continue this, even if you consider squashing deformation away from this compact space, the same story holds true that even on the compact space, your partition function, I mean, there are zero modes. So the partition function will be zero unless p equal to zero. Okay. So yeah, so S2 is very simple to see, but yeah. Yeah, so okay, this part what you were asking earlier. So one more information actually which will be again important, and okay, these are just details of the whole calculation. I'm not so sure how much it is important, but just to mention that what one also observed, let's say this squashing which we have considered, that on S2 which we have is that the zero modes in for any P is chiral. I mean, in the sense that if you consider P to be positive, you have you have a left moving or right moving, sorry, some positive chirality. And if you have negative P, then you have negative chirality. And what is interesting, what one can show is that if you consider this squashing, which we have considered, this squashing, of course, doesn't change the number of, index of the operator. So therefore, the difference of chiral zero modes still remains the same. But even this squashing doesn't change the individual numbers. In other words, even if you consider positive P, then the positive chiral zero modes remain positive chiral zero modes. They evolve, they change form, but still only positive chiral zero modes. And for negative P, still have negative chiral. And that this although it is just a technical detail, but it is important for later calculation. So actually, one way of seeing this is very okay. Fast forward way is that this squashed metric, one can do some kind of conformal transformation, some coordinate transformation, and one can show that this squashed metric is same as just S2 after some conformal factor. Okay, and then if you look at how the Dirac operators change under this conformal transformations, okay, so you just simply see that if you know the zero mode of one, then you can determine the zero mode of other. In particular, the chirality remains the same. Okay, so that's how one can get a idea that even though you're considering this squashing, but if you start with only positive chiral zero mode and zero number of negative chiral zero mode, so then the structure remains the same. Okay. Okay. Yeah. Actually, anyway, this is the explicit form of zero modes one can obtain, and there's a squashing dependence. It's okay. That's not important. So okay, so now let me come back to the calculation. What Joseph was asking. So so if you consider just given us some topological sectors, so what I'm going to do here is that so in a given topological sector, I split my field in terms of some mu, which carries that topological information, and then the rest of the fields have zero topological sector. So basically, the rest of the decomposition has just a pure gauge, and then this is transverse. Okay, and all this topology information is contained in here. Okay, in other words, this mu is what we call the monopole background. So we have this, and you see that I mean, as I was saying that the smoothness has to be maintained, and that's why there is a factor of 1. Okay, this one factor is essential so that we have a smoothness at the north pole.
Sorry, can you just, in this language, like, you were saying that only the equal to zero, contributes. What's that statement? Equal to
for in what? In partition function?
in the partition function?
P not P equal to 0, yeah.
So is it easy to see that? Like, so currently you explain it, but I kind of
easily, I mean, in the sense that because you remember that when you consider partition function, so you have to integrate over the fermions, right? And then you are integrating over gauge field.
Right.
So for any P in a topological sector, then this carries 0 modes. So if you consider anything, if there is no operator inside, okay, then this partition function will be 0. 0. If there is 0 mode, fermion 0 modes.
There are operators, then that's off the.
Yeah, exactly. So I need to turn on some operator to absorb these 0 modes. Okay. So then that will get contribution for non-zero P. Otherwise, for partition function alone, it'll have a only non-vanishing contribution for P equal to 0.
But if it's like if it's a one-point function, you can't go to P, right?
No, you cannot go. Right, exactly. So that's the part that for every, so that's the another coming to question, another realization that for any operator, if you go, you cannot have any arbitrary sum. It has to truncate somewhere. So that's the so it is always a finite sum.
Okay, it's a finite sum, but then how would these sectors would then also be present in the bosonic side, right? Because you have a compact boson, then the very sets, like that be a map from somehow. Because the compact boson, it will be a map from a circle to circle like that. Should I think of it like that, or
You mean compact boson on a sphere? You mean?
no? So it's from a sphere to a circle. So here also
Okay.
the map, the Z comes from a map from a sphere to a circle, right? That is Z.
Z, sorry, what is?
I mean, here you have E1 gauge field.
Yeah.
So that's the group manifold.
Right, exactly.
And
The
the
P,
space time is S2.
yeah, so the P is actually that winding number.
P is the winding number
of
the S2 on the circle, right?
Of S, yeah, exactly, yeah. So the circle equator to the circle, yeah. Let's say equator. Oh, yeah. Anyway, but tell me.
So on the bosonic side, how should I think of this this sector like this? Is there a geometrical way of thinking about these sectors?
Actually, to be honest, actually, I really don't know exactly because okay.
I mean, one
Point is
that
that-
comes to my mind is like, you're saying it's a compact boson.
Yeah.
So the target space is like a compact, circle.
But actually, point I'm just confused. Maybe you can understand. If you consider the let's say boson on a sphere, I think this compactness really doesn't matter. Because the circle shrinks, right, on the S2.
No, but
So if you consider smooth
here,
scalar
it's
field,
the other way around here, right?
no, you're talking about the bosonization part, right?
Yeah, okay.
So in the
Right.
bosonization part, actually, there cannot be non-trivial binding number because otherwise, because then it will be not smooth at North Pole and South Pole.
So, but how do you sectors then?
Yeah, actually, that's a good question. This was the question which I have actually. That how come it happens that there's sectors here and suddenly everything is trivial. So I don't have an answer to that question actually. So actually, to begin with, what I really wanted was some sort of refined partition function, which are sensitive to each of the sectors, and somehow then you see under bosonization.
Sector by sector partition function.
Yeah, sector by sector partition function.
But then you have an argument where, the
No,
partition
so of
function
course,
is
not this partition function, but something different, refined partition function, or some refined partition which can capture all these sectors, some label. Okay,
good.
that I don't have. And that could explain that how is really mapping taking place actually, how the map is taking place. Yeah. Right.
But the configurations on that side is solitary, kind of. Right?
No, if you consider massless, then it is just a trivial scalar. A massive one is more interesting, but where you see solitons, San Gordon, etc. But even a massless case, actually, I fail to understand how it is happening. But yeah, I mean, yeah. Okay. Anyway, so there's some. Anyway, I don't want to go into much technical issue. So basically, okay. So this is how one can decompose, and then we have to do path integral. So this is just a pure gauge mode, so we can forget about it. So effectively, it reduced to, when you integrate all the gauge field, it reduced to sum over p and integration of phi. Right, that's the thing. Sorry, this phi and this phi are two different. So this phi is a phi of no transist component, and this phi is so okay. Anyway, so this was okay. Just one more thing I want to emphasize. Again, this is just a very technical part, but so you notice that I have this term. This is very funny looking term, which is linear in phi, and somehow you feel that it will generate tadpole. Basically, it coming because I have made this choice of the topological configuration. If you look at the right configuration on a squashed sphere, it is actually really much more complicated than this one. Okay, but the reason I chose in this form, which is which is exactly same as the sphere, because then calculating the Fermion zero modes or calculating some one loop calculation just for this are a little bit easier. On the other hand, but those are easy, but then the price I have to pay, that I have to deal with these linear terms. Okay. But yeah, other than that, it's okay. Yeah, so anyway, so one can write down the gauge field part, kinetic term for this decomposition in terms of some theta field, which is just some this linear combination, non-local linear combination. And now let me come back to the fermions part. So you have this fermionic part, and then what I have done, just simply replace the gauge field by just this decomposition. And now we have to do the calculations. So I'll say that partition of values. Okay. So let me just come back to this here. Okay. Okay. So let's. Okay. So the first task would be is to again do the same kind of calculation that you integrate out the fermions. Okay. But again, the issue here is that now if you're integrating out the fermions, and it will generate some sort of effective action for this field phi. So what the effective action will look like? So again, the point here is that this phi you can remove by some chiral transformation. But this is a too fast argument actually, because as I emphasized that on the monopole background you have a zero modes, so you have to be little bit careful. So what will happen that if by doing this chiral transformation, you generate this kind of term, which is very similar to what I had mentioned earlier. But then since they are zero mode, so you have to do a bit more careful. So on top of this, there is some extra contribution, and the extra contribution come from this part here. So this part, okay, so let me just mention what is this. So this, what we are doing calculation is just doing the fermionic one loop calculation. Okay. Okay, so there are 2 points I mentioned. So at this moment, I still keeping P non-zero, even though for non-zero P, I have a zero mode. But what this quantity represent is just the integration about the non-zero modes. Okay, there's still integration of a zero mode left, which you have to do this. But right now, this result is just for the integrating out the non-zero modes for the fermions. Okay, we have to still do the integration over the gauge field, but right now it's just the integration over the fermions. So this is this anomaly part up to this this problematic, not problematic, but irritating term, a linear term. But then there's another term here, which is really coming from the zero mode part. Okay, so you have to be, so this N is a matrix which are constructed out of the zero modes, and that because what we have to do now, and one again sees that even if you have term phi, then this operator still have a zero mode. Okay, so so not just in the presence of monopole background, of course it makes sense because both has the same topological sector, even whether you mean presence of W phi. So this gauge field has the same topological sector. So and the number of zero mode again the same P. So only thing is that so the only thing what happens that now if you're doing the integration over this Dirac operator in presence of this field phi, then the zero mode will be function of the field phi. Okay, so that's how this contribution, and this contribution was this is same as this one, but phi equal to 0 means and this contribution is the contribution in absence of field phi. So basically, so what I'm trying to say here that this is the result of integrating out the non-zero mode of the fermions. It consists of 3 terms. One coming from the zero mode part, another term which is somewhat anomaly term, and another term which is in the absence of phi field. So just one loop calculation on the monopole pack. Okay. Okay. Yeah. So this is the partition function. Again, sorry, there should be still an integration here, which is integration over the zero mode. Sorry, I had forgotten to miss this here. So, but nevertheless, after integrating out the fermions, what is left over is the integrating out the phi field. And now, if we focus on, let's say, P equal to 0, which is really the partition function, because P equal to 0, we don't have a fermion zero modes. So in that case, we can compute the partition function. So you see that the partition function comes out to be of this form. Okay. Now from this partition function, now you can see somewhat a Bose-Nash duality. Okay. So this partition function, you see here. okay, so this come from some Jacobian, because the gauge field we transferred to pi field. So that is a Jacobian part, but nevertheless, so this grad square is actually really killed by this piece. So effectively, what is this one is a scalar field with mass e square over pi. Okay. So this is what somewhat essence of this bosonization duality, except one important caveat, and that is that
Sorry, I didn't understand that. What happens to the number square? This is a determinant.
so this determinant box operator is coming because when we do this LU to this decomposition, this decomposition, then this becomes a Jacobian factor. Okay, so that Jacobian is just this box.
Okay.
This quantity. Okay, so you are left with the phi integration, and then the action for the phi field is just this one.
1 by the Asha. Okay.
Okay, so so this I'm just saying that this one of the grad square just cancel out. So effectively,
This is another way of seeing that, the scalar transformation will be anomalous, and here you are tracking the anomaly from the measure to the Jacobian. That's why we are cancelled. But yeah, sorry. Maybe one.
Okay, okay, yeah. So actually, just wanted to mention one little caveat here. So although this is equivalence, but notice that I mean, it is not like suppose if we say that the fermionic theory, and then you have a bosonized version, and they are equivalent. So let's suppose if you want to compute the partition function, then we say that the partition function of bosonic theory will be same as the partition function of the fermionic theory, or let's say Schwinger model. You note that this is true except just this factor. Okay, so what I meant to just say that okay, okay, so this bosonization still holds true, but there is still one factor which if you naively do this, let's say flat space bosonization, if you just naively put it on a sphere and do the computation, you'll miss this factor. Okay, so this is a factor we are getting from the doing the fermionic analysis in terms of this, yeah, so one has to keep this factor, which is a function really of the squashing parameter B.
But if you take B out to 0, that
Yeah,
goes to 1.
yeah, that goes to yeah, this goes to 0, this one, yeah.
Yeah, but it's a normalization of the partition.
That's true. So this is a normalization, but then it's not like the partition function of Schwinger model becomes equal to the partition function of this thing. There's this some
On the squashed. On the swap.
yeah. Okay, so I will just point out that most of the discussion holds true for any curved spacetime. Yes.
And because in 2D everything comes as a compromise.
Yeah.
We expect that the partition factor will get a.
Some extra, some other
Overall.
factor, or factor.
Overall.
Yeah, that's true. Yeah. Anyway, so yeah, so that's the thing. Anyway, so actually, okay. Another thing I just wanted to emphasize that you notice that the okay, so we can now all this thing right now exactly in the coupling constant, exactly in the squashing. Okay, of course, then you can also do this calculation. Let's say because full spectrum is not known for the squashed space. So what we did here is that we calculated in the squashing expansion squashing, and this is as I mentioned in the first slide. That is the 1 point function of the energy moment tensor on the sphere. Of course, there's a mass mu which is e square pi, and yeah, so this is the contribution to the 1 point function. But what is important is that this computation is perturbative in B, but exact in coupling. So mu is in the so it is this expansion is exact in coupling. So whatever the term appearing here, this is exact in the coupling. Okay. Okay. Yeah, anyway, so now let me come back to the 1 point function. Or let's say yeah. So you can repeat the same analysis with the operator insertion. And as pointed out, that now the infinite sum over top of it will truncate it depending on the Fermion zero. So, for example, let me directly come to okay. So let's suppose if you are interested in how much time do you have?
12 minutes. 50 minutes.
1-5.
1-5.
Okay. Okay. No. Yeah. So basically, just wanted to say that if we now do the computation, so okay, for example, let's suppose if you consider 2 point function of the Greens of the fermions, you see this sum over topological sector is truncating. It's truncating only p equal to 0, p equal to 1, and p equal to -1. The higher order terms will be 0 because we don't have enough number of fermions to absorb 0 modes. Okay, so therefore we have just only 3 terms to calculate. Okay, yeah. Actually, I was just going to give an insight, but I guess I have convinced already, so I don't need to give this details here that how it is happening. So let me just write it down here, since I don't have much time. There's a question answer. So okay, so let me come to the condensation actually part. So so the important thing happens that let's suppose this chiral symmetry breaking, right? So if you want to see really the chiral symmetry breaking, because my original theory has a massless, so there was a chiral symmetry, but this also breaks the chiral symmetry. A Schwinger model, you can see the chiral symmetry breaking, and the way you see that we can compute this condensation. Okay, side by side. Okay, and what one finds, just tell you the result that again this 1-point function you don't have to calculate for all p. It receives contribution just p equal to +1, because p equal to -1 will have a negative chiral 0 mode which cannot be absorbed by this one. Okay, so so therefore it receives contribution only from p equal to 1. P equal to 0 it cannot be absorbed. There is no contribution because remember that we are computing the traced quantity, and the trace of Harmony-Green's function is 0. Okay, so therefore only contribution comes from p equal to +1. Okay, anyway, so that's another simplification occurs. So yeah, so actually, just coming back to Nilay point. So this thing, what is happening that because Fermion 0, that will be missing if you consider just a complex scalar field coupled to gauge theory. So there you'll have to have all the sum about p, etc. for the calculations. Anyway, so okay, this is okay. So I'll just mention that this looks a little complicated, but to be honest, actually, the answer which you want to look at is just the first line. It's complicated as Jyotirmoy's definition that it is not coming in the one line, but the fact is that this term is a stupid factor. It's just arising because of all those tadpole thing. You can really think of that this part is just part of this calculation. So okay, so just let me explain this part. So this part is a contribution just on the monopole one loop calculation, monopole background of fermions. This is just a 0 mode part. The 0 mode because remember that this receives contribution from the 0 mode. So so this is a 0 mode wave function, just the eigenfunction. This part which you receive by integrating out the scalar field in that contribution, and then there is this some volume factor. Okay. So this is a Green's function for the scalar field with the mass used to attach. This is a G mu, and G here is just for massless space. Okay. Anyway, so these are small technicals. Yeah, so one can one can here see how the S2 answer look like by putting squashing equal to 0, and also you can see how this expression looks like in the flat space limit, which is effectively here the gauge coupling going to infinity. This is what the condensation look like, and yeah, so we can also do this small expansion b square again. This first term is actually this is nothing but the 2-point function of energy mounted tensor with the condensate, and this is exact in the coupling. Yeah, so one can also do the Wilson loop calculations, and one can show that this goes like a perimeter law. So therefore, this really is a deconfined phase. So yeah, so I'm not going to this, but one can do this calculation. Yeah, so this is how the Wilson loop goes. So there's some summation involved which we could not able to do it, but yeah, one can numerically see how this correction changes with the coupling. So this was the Schwinger model, but one could consider some other deformations, okay, which is also exactly solvable. For example, one can consider Thirring model, Schwinger Thirring model, and you can see how this thing, although it is quartic, but again it is solvable, and the reason is that yeah, I mean, just a small trick one can do is that you introduce some vector field which couples to this cyber gamma mu psi. And then again, you're doing the same kind of massage. You will find that one can completely integrate out. Yeah, so maybe I'm rushing a little bit, but the bottom line here, let me just say the bottom line in this Schwinger theory model. The bottom line here is that that effectively all the calculation which we have done for Schwinger model, it again goes through it as it is, except the only difference arising is that my scalar field get a mass which is corrected, okay, which is mu tilde becomes mu plus 1/2 lambda over 5. Okay, so those Thirring, this lambda is a Thirring coupling, this here the Thirring coupling, and that just corrects the mass for the scalar field. So again, the same kind of bosonization is happening, which you see that Schwinger Thirring is same as again a massive scalar field, but the mass given by this one.
That's like just maybe like the gross.
This is like
The gross kind of.
gross.
If you just look into the phi and psi sector,
Yeah,
it's like giving a mass transfer.
I see.
It could be.
Maybe I don't know what is gross in it. Gross in which
Gross.
I see.
Maybe.
Okay. Anyway, one can also do the same kind of calculation for the condensate. It is almost exactly same as what Schwinger had, except that the somewhere we get this terms 1/1 plus 2 lambda over 5. There is some extra contribution, etc. So other than that, one can go through the same, and same thing happens here again. That you have a topological sectors, and the topological sectors are truncated depending on the number of zero mode you absorb. Okay. Anyway, okay. So I hope I'm not taking much time.
No.
Yeah. Okay. So yeah. So okay. So I don't have very much summary here, but except that the whatever the question which you wanted to understand, you couldn't do it anything much progress. But just we wanted to see how in one example where we can do the computation explicitly, how the things working out, how is it becoming something like exactly solvable. So yeah, so of course, so we did it for massless case, this Thirring and Schwinger model, and this squash sphere is just one example of doing it, but our calculations actually, in fact, is true for generic curved space, but squashing where we can do some calculation very explicit, but most of the result is straightforwardly can be extended to any compact space. And okay, so the obvious thing next is going to much more richer thing, which is a massive theory and also non-abelian case. And again, going back to the same problem, that how really the bosonization duality works. How come such a complicated things become suddenly trivial?
So just going, I don't know, direction, but maybe you should like ask later. So going on, can I ask a question?
Yeah, sure. Because still we have time.
So if I just go by this thing that you mentioned, e to the power minus. So if I relate it with some chemical potential corresponding to P.
Yeah.
Okay. So if I just put that into the particle function, that will weight the different sectors differently, right? So
you mean no, but
it's like P is like some momentum operation, right?
P is some P is why P is a momentum operator? P is a momentum operator. What do you mean momentum operator? P is a monopole, right?
Yeah, but can't you think of P as some kind of derivative? Locally, you can't think of it.
P means derivative idea. P is just integers.
Yeah, it's integer. It characterizes the various sectors.
Yeah.
So if you have a term in the Lagrangian, which is very naively.
Yeah, exactly.
Mu times P.
P, yeah, exactly. That's true. Yeah, that's exactly. That's what we are looking for.
So, but then so this is a monopole operator. Is that possible? Like putting a monopole operator into the Lagrangian.
But we have this is the somewhat monopole operator. We have turned on the monopole operator.
Put a chemical potential in front of it, like mu times K.
Yeah. Okay. So
while evaluating the partition function.
You're right.
And then you just do the map. You will get something on the scalar side.
I'll give you something interesting about it. That
Let's do the design that normals.
Instead of doing it as a background.
Yeah.
I mean, just put it in the partition function.
Okay, actually, I'll tell you something. So if we consider the massive one, let's suppose the massive one. So the mass deformation, if you add. Okay, now you see that this mass deformation. Sorry. If you can see this mass deformation, now you see that if we expand this, okay, let's say partition function, why it is a massive one, it becomes a trickier one, is that if you consider m psi bar psi, and let's suppose, so of course this doesn't have a zero mode because fermion zero mode, because now we can see massive perturbation. But let's suppose I think of mass as a perturbation parameter, okay, so that I can write it as sum over n, okay, and some psi bar psi. Okay, so this and now we have expectation value. But now notice that I'm generating all those fermions which will absorb the fermion zero modes. So partition function now will receive contribution from all the sectors. Do you get the point? So earlier, because see,
I see that, but let's say, okay, so this, you are saying that with the mass, partition function will receive contribution from all the sectors.
and there's some m power k is actually k becomes like a really p. Okay, but the problem here is that so this is the one way to look at this problem, that the mass, but then of course it becomes a really infinite sum.
Yeah.
Okay.
But in the mass-based case, if I just want to, weigh it with respect to this calculation, I mean, that is just. Because just deform the appearing with the monopole operator.
Right.
Putting in some
Some chemical potential. Yeah, I don't know how to do it. I don't know how to do it, but yeah. Because it has to absorb the fermion zero modes.
Coming to put direct here, probably not, right? I mean, then you could just use the same eigen functions with the expanding. Probably not. That's not. Okay, we should.
Other questions? We have time for questions. All right, if not, let's end this session.